There we go.
Okay. Hunter? Number 16? Sorry, calling you mayor.
Please.
Anyway, what?
Number 16.
Okay. So here's the deal. So you got an idea of gas, right? Frictions. So here's what's important. And you have to be able to figure out the subtleties of what happens on these problems. So if you look on 16, is in the cylinder is a frictionless piston, right? So what that means is this, is that you can change the volume, okay? So since you can change the volume right away, you know this thing is not going to be an isometric or isovolumetric. It means the same thing. So in other words, we can change the volume of the system. So then you got the pressure, right? During the process, 5.02 times 10⁻⁶ joules is added to the gas. So now here's the thing, okay? Understanding thermodynamics is all about understanding prepositions. So here's this syringe, okay, right? So you have a numeric value of Q. So what I'm giving you is Q, because Q represents energy added or energy taken out, okay? So, and you have to understand how to do the prepositions. Because on the test, which is coming up on Thursday, by the way, if you want to plan the rest of your class. So we've got a lab today, we have buoyancy tomorrow, review on Wednesday, the test over energy and buoyancy is on Thursday, review on Friday, written final Monday, 3 days of lab final, last Friday we'll kick back, okay? So if you want to plan your social calendar, that's what you got going. So, here's the deal. When you add energy to something, what do you think is going to happen to the internal energy of the system? It's going to increase. So Q is intuitive, okay? Most people don't struggle with the concept of Q. So in other words, I'm going to take this and I'm going to add a certain amount of energy into it. What you have to decide is if that value of Q is going to be positive or negative. Okay, so what is it? Positive or negative?
Positive.
Positive. I'm adding energy into it, right? So keep in mind that delta U also equals Q plus W. So this is like your bank account here. Okay, the delta U is your bank account. So I'm adding energy to the system. Now, here's what's important. Then you're told that the volume changes from 10 cubic meters to 18.2, right? So here's the deal. What's happening to the volume of the system? Is it getting bigger or is it getting smaller? Bigger. Anytime the volume gets bigger, okay, that means work is done by the system. It costed energy, okay? So anytime you see the volume of something getting bigger, that costs energy, okay? Which means, and the code word is that its work is done by the system. If work is done on the system, like, if you remember what I did with the fire syringe when I pushed that down, okay, I did work on the system. That greatly increased the delta U because I had a positive W. So that means I had a positive delta U. I compressed that thing very rapidly. I greatly increased the internal energy of the system, and we lit that cotton on fire. Okay? So, work done on the system equates to a positive W. Work done by the system means the volume gets bigger. Work is going to be a negative value. Okay? If there's anything that you begin to memorize for this test on Thursday, it's that. What the sign of Q is and what the sign of W is, and the prepositions associated with that. So, here's the deal. So here on 16, you've got to find the work done by the gas. Okay. Well, work is going to, there's two ways to calculate work. One is that it's negative P delta V, and the other one is nRT natural log VI over VF. Okay? Those are your two ways you can calculate. So what you have to decide is, wow, what's going to happen on this one? So here's the deal. Could you even use, with the information that you have on 16, could you even use this equation even if you wanted to? No. Why not? You don't have the number of moles, and you don't have the temperature. Okay? You could not use this equation if you tried. Okay? There is no way you can use this equation. It's not there. The only time you use this equation is when you have an isothermal expansion or compression and you're trying to find the area underneath the curved line. Okay? Now, you can use this one. You know the pressure.
Yes.
You know the change in volume.
Yes.
Now, here's the significance. This is why you have to have that negative sign lurking out there in front of this deal. Okay? That's the significance of this. So when you look at this, this is going to be V minus V naught. So that's going to be final minus my initial. So the volume final is bigger than the initial volume. Okay? So that means I'm going to end up with negative work. So here's what's happening. If you go to like the analogy of my passing, I'm going to leave Mary a bunch of money. But she's got to take some of that money and build something. Okay? So I'm giving her a lot of money, but she can't keep it all. Some of that has to go towards making the world a better place. Okay? Good with that idea. Now, if you contrast that, if I had said I removed X amount of energy, okay, so in other words, I put it in an ice bath, and I made the volume get bigger, then both of the values would be negative, and I would greatly reduce the internal energy of the system. Or if I dumped energy in, and I compressed it, that would greatly make the energy go up. Okay? So you can have, it's like it's 4 permutations. You can have positive Q, positive W, positive Q, negative W, negative Q, negative Q, positive W, negative, and a negative. So basically figure out which ones are adding to the internal energy and which ones are taken away from it. Okay? So if all goes well on number 16, the first answer should be something times 10 to the 5th, and your second answer should be something times 10 to the 6th. Well, cool. Anything else? Mary?
Number 17.
Okay. So, here's the deal. So, you got a pressure volume graph, right? So, let's talk about constant pressure. So, how does a constant pressure system look on a pressure volume graph? Horizontal line, right? So, on this one of two things can happen with this line. Okay? Either you're going to go from a bigger volume to a smaller volume, or you're going to go from a smaller volume out to a bigger volume. So what's happening here? Big to small, small to big. Big to small. Okay, you're starting out here at like 0.01 cubic meters, and you're ending here at 0.005. So if you have the syringe, okay, what would you physically be doing to this system? Yeah, you're crunching this thing down, right? So when you go from here to here, you're making this thing smaller, right? Now, if you look at PV equals nRT, pressure staying the same, right? Okay, pressure staying the same. It's isobaric. What's happening to the volume? It's decreasing. So what's the only way this can happen?
Temperature decreases.
If the temperature also decreases, right? So I've got to drop the temperature, which means what are you going to do? Physically, what would you do? Yeah, you put it into an ice bath, cool it down. Okay, like that's what you're going to do in the lab today. Okay, you're going to put stuff into cooler systems. You're going to see what's going to happen. So on 17, you got the initial volume. Okay, draw the process on this, right? Now, so then we basically compress it. So we're at this point. Then what's going to happen? Then it's going to expand back to its original volume. But it's going to expand isothermally. So how do you draw an isothermal expansion? It's going to be one of two things. It's either curve up like this, or it's going to curve down like that. Which one?
Down.
Yeah, because now you have a constant temperature, so you have an inverse relationship between pressure and volume. That's all you have to draw. That's it. Now, which one is going to involve more work? The isobaric compression or the isothermal expansion? Which one's going to involve more work?
Isobaric, right?
Why?
Because the isobaric has a bigger area.
Yeah, your isobaric line has this whole area up here, your isothermal line is always going to be down here. So isobaric is always going to involve more work than isothermals do. Okay? Good with that. Now, on 18, okay? So here's the deal. I want to find the work done by 0.1 moles of gas, temperature, right, expands. So here's the deal on 18. On 18, could I use work equals negative or work equals? Could I use work equals negative P delta V on number 18?
No.
Why?
You don't know the pressure.
I don't know the pressure, okay? I can't do this even if I try. Now, here's the deal. You've got a constant temperature. So what do you think is going to happen? What are you going to use? It's a constant temperature. You're going to have an isothermal line.
Yeah.
So this is where you're going to work equals nRT natural log VI over VF. So what you should see on 18, your work should be something times 10 to the second. Okay, not very much work. Of course, you don't have very much volume. And you're not changing it that much. On number 8, okay, here's what you have to understand on number 8. Let's talk about that, even though no one's asked about it. So even though you don't have to draw the graph, okay, you have to understand that this temperature and energy line, okay, this graph is going to go something like this, going. So here's the deal. You're going to start here at minus 10 degrees Celsius. So so if you think, this is what you have to visualize. You're going to end up at steam. So what's the first thing that you've got to do to this ice? What do you have to do?
Melt it.
Or to melt it? No, you got to do something before you can.
You got to heat it up to zero.
You got to get the temperature up to zero. So anytime you have a slanted line on here, you're going to use Q equals M C sub P delta T. This energy is going to create a change in temperature. So when you dump energy into a system or remove energy, it can only do one of two things. It's either going to be in the formation or the breaking of bonds, or it's going to go to increase the temperature of the system. Okay, that's it. It's got to be one or the other. So on this system, you're going to raise the temperature from minus 10 up to 0. Use the specific heat of ice. Do not use the specific heat of water. Okay? You have to use the specific heat of ice. Now, once it plateaus, then what's happening?
Phase change.
Phase change from a solid to liquid in this case. So when you have a phase change involving solids to liquids or liquids to solids, what do you use? Latent heat of vaporization or latent heat of fusion? So the latent heat of fusion. So that's going to be Q equals M, latent heat of fusion. Go it, find it. It's like 3.33 times 10 to the 5th joules per kilogram. Now, after it's all melted, then what are you going to do?
Raise it up to 100.
Well, you got to raise it up to 100. So you can go from 0 up to 100. So now you're going to use Q equals M delta T C sub P again. But now you're going to use the specific heat of liquid water. Okay? So that's going to be your third calculation. Now, once it reaches 100, then what's going to happen?
It's going to start to boil.
Then the temperature is going to stay constant because all that water is going to boil. So then you're going to use this Q equals M, but instead of using latent heat of fusion, you're going to use latent heat of vaporization, which is about 10 to the order of magnitude bigger than the fusion. So that means it takes a lot more energy to boil water than it does to freeze it or melt it. Okay, there's a lot more energy involved there. Then you're going to use Q equals M C sub P again, but then you're going to use the steam. So you're going to go from negative 10 to 0, 0 to 100, 100 to 110. But you've got three different specific heats. First one you're going to use the specific heat of ice. Second one you're going to use the specific heat of water. Third one you're going to use the specific heat of steam. Okay? Then you've got your two latent heats. So if all goes well, on number 8, you should get something times 10 to the 6th.
So can we not use Because I use change of U equals 3/2 and our change of T.
It's not a gas.
Oh, that's only gas. Alright, yeah.
Oh, God, no.
I found the moles, and then I just did that.
No,
Okay.
no. No,
No?
bad. No. It's not a gas.
I'm erasing it. I had 5 steps.
Which step was that?
I changed it from, I found the moles, that's step 1. And then I found change T, step 2.
Which change in temperature?
I did -10 plus 273. And then 110 plus 273.
So you took this from ice at -10 in one step all the way to steam at 110.
That's exactly right. I understand. It made sense.
No, it didn't.
It did. I had everything I needed.
It's not a gas.
Where does it say it has to be a gas though?
Okay, what's R? No. What's R?
That's
The ideal gas law constant.
I don't recall.
Not the ideal solid law constant.
I don't recall it. Nope, it is not labeled on the big dog equation.
What's the only time we've used it? In gas laws?
I mean, we used it in this
Now-
topic.
Repent.
I
Repent and do no more. Okay, repent and do no more. Okay, anything else?
Just a question. No,
Okay.
I just concept-wise. So on that number 8, so no matter how quickly or slowly you supplied the amount of energy, it would just take that much.
That's just a function of the wattage. Yeah. So,
Okay.
Anything else? Once, twice sold, boom.
All right. Eli likes to play with the zoom function.
He does.
Okay, I wasn't looking at it this time. I was just messing with it.
Okay. All right, so what you're going to do in this lab is going to see if this whole kind of ideal gas law thing works, and we'll explain it in terms of Timmy and all this good stuff. Okay, so here's what you're going to do on the first part of the lab. Now, there's 3 distinct parts. So you've got this pressure sensor. This is just going to plug into a lab quest, okay? They're over there, plug them in. So the first thing you're going to do is that you're going to fill this thing up to a volume of 5. And make sure that the 5 is based upon like that leading edge of that black plunger. Not the tip of it, but that leading edge. Okay, so that's what's going to determine that volume on. So you're going to fill this to 5, and you have to pay attention to the sequence. You're going to fill this to 5, and then you're going to screw it onto the pressure sensor. Now, you're not like tightening a lug nut on an Indianapolis 500 car. Okay, don't ask me for a wrench. Okay, no. Okay. Just get it snug, that's all you have to do, okay? This isn't like the world's strongest man competition. So, just get it snug. Now, I actually kind of revamped this lab yesterday, and I forgot to check out a couple of things. So when you get to section 1.1, it's going to tell you to keep this data, and you can store it. Don't worry about it. Just write down the data. So what's going to happen is you're going to fill this thing up to 5. You're going to get a reading on the screen. It's going to be in kilopascals. It should be probably around 95 to 100 to start with, okay? So, fill it to 5, screw it on, get the reading. Then, what you're going to do then is you're going to pull this back until it reads 7, okay? And then you're going to let it stabilize, you're going to get another reading. And you're just going to keep going back and back and back and back and back until you get all the way to 15. So you're going to start at 5, you're going to go by 2s until you get to 15. Okay? And do not disconnect this at any point. Once you've got it sealed up and you start at 5, it stays at 5. Okay? So that's going to go relatively quickly. Pull it back, let it stabilize, pull it back, let it stabilize, boom, you're off to the races. Now, on the second part, and this is relevant to your vaping generation. So,
Hell yeah.
yeah, who put the bathroom stalls in the vaping room? Okay,
It's actually the jewel room. That's what it is.
jewel room,
Yeah.
jewel room.
Yeah.
Okay, so what we're going to define as a puff, okay, because that is just, I tried to find other words for it, and just, this is just what I said. So what you're going to do is this. So you're going to set this thing, and you have to pay attention to the sequence. You're going to set the plunger at 3 milliliters. So we're going to define 3 milliliters worth of particles as a puff. So then you're going to screw that on, okay? And then you're going to pull that back till it reads 10, okay? So then you're going to let it stabilize there, get a reading. Let it go back. Then unscrew it. Then take this, pull it back to 6. So now you have 2 puffs in here, okay? So then you're going to screw that back on, pull that back to 10, get a reading. So the common volume on all of these is going to be 10 milliliters. So then you can do that again, go to 9, okay, which isn't any big deal, screw that on, pull it back to 10, get reading. Now, once you get past that, so like when you get to the 12, then you actually have to compress this thing back to 10. So up to 9, you're pulling it back to 10. Past then, you're pushing it back to 10. So you're compressing some, and you're making some expand. But the common volume is going to be 10, okay? So you're basically putting more and more and more and more Timmies in the same size classroom, okay? Now, the third part is going to be the hardest part, and it's going to be the most time-consuming, because that's going to require hot water. So the first thing you do when you get into, take like a 400 milliliter beaker, and there should be some laying out there, and get that about, most of the way full with water, and then turn that on so that that thing begins to heat up. So that is before you even start the lab, because it takes so long for this water to heat up. So the first thing that you want to do is crank up the heat and get that water started to heat up, okay? Once you get done with that part, okay, then for the next part, you're going to unscrew that syringe, and you're going to put on this one, which has a long flexible hose on it. So you're going to put that on here, screw that on, and then now you're going to use a test tube, and now we're going to keep a constant volume. Okay, so this is going to become an isometric process. You guys are going to keep the volume the same. So what you're going to do here is you're going to take this, and you're going to start off with hot water. Now, the water doesn't have to boil. What you want to do is put a temperature probe in there and get that water to about 80 degrees-ish. Okay, something around 80 degrees. Then put that in there, and then once that water kind of stabilizes its temperature, put that in here and let it sit for a couple of minutes so that the temperature of the gas inside of here matches the temperature of that water. Now, you're not going to take the temperature of the gas inside of here. You're only going to take the temperature of the water, but you got to figure it's going to be the same temperature. Okay? So after that stabilizes and you get a good reading, then you're going to start to add some ice into that beaker. So then you want to drop that temperature down. Now I've got a tub of ice in there. So you're going to drop that temperature down about 10 or 15 degrees Celsius, okay? Just don't get it too cool, because then you've got to go through the process of warming it back up. So you want to drop it down about 10 or 15 degrees. Then once it stabilizes again, then get another reading. And so what you want to do is you want to keep dropping the temperatures and dropping the temperatures. Now, eventually what you want to do is, and you can actually use like room temperature as one of your readings, okay? You can use that as like, oh, here we are at room temperature, this is one of the readings. So what you want to do in an ideal world is that you actually want to get a temperature like below room temperature, or maybe you get it on like 5 or 6 degrees Celsius, so that way you get a nice comparison. So you got like one below, one at room temperature, and then a bunch that are above that. So, and it doesn't have to be exact, but you want about a 10 to 15 degree temperature range in between those values. Now, whatever you do on this last part, not to sound like Indiana Jones in The Last Crusade, but do not break the seal, okay? Do not break the seal. Because if you do, then you're going to introduce whole new sets of systems of particles and everything else in there, and you're going to have to start all over, okay? So on part 3, don't break the seal. Okay? Got it? Okay. Now, you got a bunch of stuff that you're going to have to do. Trust me on this one. You got labs to draw. This is why I did the crinkle staple. When you get to question number 4 on page 1-4, this is some information that you're going to need. 1 cubic centimeter equals 1 times 10 to the 6th. That's cubic centimeters. Cubic centimeters. The molar mass of nitrogen is 28 grams per mole. The molar mass of oxygen is 32 grams per mole. And the percentages that I gave you, this will make sense when you get this. The percentages that I gave you are percentages by mass. Okay? That's going to be an important part when you get to this. It'll make sense when you get to that problem. But the percentages are by mass. You need this conversion, and then you need these conversions as well. And if all goes well, here's what your order of magnitude should be: 10 to the negative 4th, 10 to the negative 5th, and 10 to the negative 4th. So if all goes well on question number 4 at the bottom of page 1-4, this should be your order of magnitudes on your answers. Okay, there's going to be a small number of moles within that system. Okay, go. Start to heat the water first. The other data collections goes pretty fast, but the water one takes the longest.